So here we have a mass spring damper system. Now many people, this is their introduction to second order systems. We did this in reverse format because I want you to know that while this is the poster child for a second order system, it is not the only one there is. So again, if you would like to do this from scratch, draw your free body diagram, find your ODE, now is a great time to pause the video, work on getting that transfer function here, and once you have that transfer function, start the video up again. And maybe wash your hands in between, just because it's never a bad idea to wash your hands in these days and age. But make sure you're using moisturizer after, because you don't want to have cracks in your hand that can make it easier to get an illness by overwashing your hands. Okay, we are back. And transfer function for this one would be 1 over ms squared plus bs plus k. This one I'm just doing from memory because it's a very common example, but you don't have to know that by memory. So if we put this in standard second order format, we have s squared plus b over ms plus k over m. And so that puts it in standard second order format. And we can say that our omega n is equal to the square root of k over m. This may be a familiar statement to you, where you've heard your natural frequency defined as the square root of your spring constant over your mass. That is the case for this specific scenario and a couple other scenarios, but we're going to see that it's not always the case even for mechanical systems. But for something as simple as this, it is the case to the point where your book defines your natural frequency as the square root of k over m and does everything from the perspective of a mechanical system. I'd prefer to not do that since we have a lot of systems that can be second order, so I'm going to always try to think of this in terms of that a omega n squared over s squared plus 2 zeta omega ns plus omega n squared. So we're always going to keep that image in our mind, but for the mass spring damper system, especially the one we have drawn here, we have that the natural frequency is square root of k over m. A, in this case, is going to be, we can see that we want to have that 1 over m is equal to a times the square root of k over m, which means that a is equal to 1 over k. Sorry, I see what I did wrong here. We have that it's a omega n squared. So 1 over m is equal to a times k over m. So that means that a has to be equal to 1 over k. And we also have that our 2 zeta omega n is equal to b over m. So zeta would be equal to b over 2 times omega n times m. And, or if we want to go forward a step, we could see that it's b over 2 times the square root of k over m times m, which would be times the square root of km. So this is how we do a second order system. Again, in your book and the table they actually discuss second order systems just using the terms from a mechanical system. But I want you to keep in mind that when we talk about second order systems, they can be electric systems, they can be fluid systems, they can be many types of systems, but we as engineers, we do kind of resonate, which is, sorry, that was a pun in my head, because the natural frequency often is involved to the resonant frequency, which we will get when we talk to frequency analysis. But I digress. Man, I do not like recording my voice. Sorry, let's press pause for a second. Okay, so the step function for this input would just be adding a weight for our f here. So step function would be adding a weight. Okay, so I have 40 minutes to finish this up, so I will move on to the next ones and edit that out if I can. Probably can't. Good luck, everyone. Hope you are surviving through this online process better than I am.